Think about the feeling you get when you look up at a clear night sky, far away from the noise of the city. There is a deep, profound quiet. It is a stillness that feels heavy, not empty. It's the kind of quiet that makes you think. You see the pinpricks of light from stars that are incredibly far away, and between them just a vast, dark ocean. This is the great stillness of space. It is enormous, dark, and perfectly calm. For a very long time, we have thought of our own corner of space, our solar system, as a separate, safe little bubble. In the center is our sun, a steady, warm anchor. Around it, we have our family of planets Earth, Mars, Jupiter, and all the others. They follow their paths always in the same circles like a perfect, predictable machine. It feels like our home. We believed that everything inside this bubble was ours, and everything outside that bubble was other, something separate, something we could only look at from a distance. We felt alone in a way, safe, but isolated. But the universe is a very big place, and it is much more connected than we ever imagined. What if that feeling of isolation isn't completely true? What if our bubble isn't perfectly sealed? What if the universe sends visitors? We are not talking about spaceships or messages or signs of life. The visitors we are thinking about are much older, quieter, and in their own way more mysterious. They are the universe's oldest travelers. They are pieces of rock ice and dust born in other places that have crossed the enormous emptiness between the stars. Imagine a solar system very different from ours spinning around a star that is not our sun. It has its own planets. Maybe a giant planet moved and in the chaos it kicked a small piece of rock, an asteroid or a comet so hard that it flew right out of its home system. This tiny piece of rock then begins a new journey. It leaves its parent star behind and tumbles into the great dark ocean. It travels for millions, perhaps even billions of years, moving through the silent emptiness faster than any machine we have ever built. It is a cosmic messenger, a tiny piece of another home drifting through the cosmos. And then after an unimaginable amount of time, its long journey brings it to our doorstep. It crosses the boundary of our own bubble and falls toward our sun. This is not a story of invasion. It is a story of connection. It is a cosmic whisper. The universe isn't just sending us light from distant stars, it is sending us actual pieces of those distant places. This is a story for reflection, a quiet idea to think about under the calm night sky. The great silence is not empty, it is full of ancient travelers. For almost the entirety of human history, we believed our solar system was a closed, isolated bubble. Everything we could see, the planets, the asteroids, the comets, was ours. They were all born from the same cloud of gas and dust as our sun, and they were all bound by the sun's immense gravity. The space between the stars known as interstellar space was thought of as a vast empty ocean. An interstellar object or ISO is a visitor that shatters this illusion. It is an asteroid or a comet that was not born in our solar system. Instead, it was formed in a completely different star system, orbiting a different sun millions or even billions of years ago. Through some ancient chaotic event, perhaps a gravitational fight with a giant planet, this object was kicked out of its home system and flung into the vast emptiness of the Milky Way galaxy. For countless millennia it travelled through the dark, cold void. We always suspected such objects might exist. Our own solar system ejects comets and asteroids all the time. It stands to reason that other star systems do the same, but the sheer scale of the galaxy made finding one seem impossible. The galaxy is billions of times larger than our solar system. Finding a single small dark object from another star in our tiny neighbourhood would be like trying to find one specific grain of sand that washed up on all the beaches of the entire world. Scientists calculated that while many might be passing through, they would be too small, too dark, and moving too fast for us to ever see. We would need incredible luck. We expected we might find one in a century if at all. For all of practical astronomy, they were theoretical, almost mythical. We were completely unprepared for the year 2017. The first visitor, ʻOumuamua, 2017, the shock of discovery. Completely unlike anything. On October 19th, 2017, the Pan-STARRS 1 telescope in Hawaii. A powerful automated system designed to scan the sky for Earth-threatening asteroids picked up a faint speck of light. At first it seemed routine, but as astronomers tracked its path over the next few days, a chilling realization set in. This object was moving too fast. Way too fast. Objects in our solar system travel in elliptical or oval-shaped orbits. This object was travelling on a hyperbolic trajectory. In simple terms, this means it was not in an orbit at all. It was on a one-way trip. It was falling through our solar system from the direction of the star Vega, and it was moving so fast that our sun's gravity could not capture it. It was going to swing around the sun and fly right back out into deep space, never to return. This was it, the first one. The mythical interstellar visitor was real. Astronomers scrambled to point every telescope they could at the object. They named it One-Eye ʻOumuamua, a Hawaiian name meaning scout or messenger from afar. But the more they looked, the more the shock deepened. We had assumed an interstellar visitor would be a comet. We expected to see a fuzzy cloud of gas and a long tail. ʻOumuamua had nothing. It was clean, dark and sharp. It looked like a dry, dead asteroid. But its path suggested it came from the icy outer reaches of another star system. This was the first contradiction, and it was a big one. It looked like an asteroid, but it came from where comets are born. Characteristics: long shape tumbling, no coma gas cloud of a comet. As ʻOumuamua sped away from us, astronomers could only study the light reflecting off it. What they found was bizarre. The object's brightness was changing dramatically, swinging from bright to dark every 7 or 8 hours. There was only one way to explain this: the object had a very extreme shape. It was not a round ball or a lumpy potato like most asteroids. To get that kind of light change, it had to be incredibly long and thin. The most popular models suggested it was shaped like a cigar, perhaps 10 times longer than it was wide. Other models suggested it could be flat, like a giant thin pancake. No asteroid or comet in our solar system looks like this, making it even stranger. ʻOumuamua was not spinning in a neat, stable way like a football thrown in a perfect spiral. It was tumbling chaotically end over end like a bottle kicked down the street. This tumbling motion suggests it had a violent past. Perhaps a collision in its home system sent it spinning wildly as it was ejected into space. But the biggest puzzle remained its appearance. As ʻOumuamua flew close to our sun, it would have been baked by intense heat. If it had any ice on its surface, water, ice, nitrogen ice, anything that ice should have instantly turned to gas, a process called sublimation. This gas would have formed a visible fuzzy cloud around it, which we call a coma. This is the defining feature of a comet. ʻOumuamua had no coma. Telescopes looked for any sign of gas or fine dust. They found nothing. It was just a dark, tumbling, cigar-shaped thing. The great mystery, non-gravitational acceleration. Why was it speeding up? The story should have ended there. A weird interstellar rock passed by, but the mystery was only just beginning. As scientists analysed Oumuamua's path on its way out of the solar system, they found something that seemed to violate the laws of physics. The object was accelerating. It was speeding up, moving away from the sun faster than gravity alone could explain. Something was giving it a small, gentle push like a tiny rocket engine. This is called non-gravitational acceleration. This behaviour is completely normal for a comet. As the sun heats a comet's ice, the gas shoots out in jets, just like letting the air out of a balloon makes it fly around the room. These gas jets act like tiny thrusters, pushing the comet and changing its speed. But you cannot have the effect the rocket push without the cause the visible gas jets. Oumuamua had the push but no jets. It was a ghost rocket. This was the central unsolvable problem. How do you make an object accelerate without seeing anything pushing it? This single fact launched one of the biggest scientific debates in modern astronomy. The theories hydrogen, comet, thin shard, and the artificial origin debate Avi Loeb. Scientists hate a mystery they can't solve, so they propose several fascinating and increasingly wild theories. Theory 1, the hydrogen iceberg. Maybe Oumuamua was a comet, but one made of something we'd never seen before, solid hydrogen. Hydrogen is the most common element in the universe. If you could get it cold enough near absolute zero, it would freeze solid. A comet made of solid hydrogen would turn to gas very easily. And crucially, hydrogen gas is completely invisible. This would perfectly explain the mystery invisible hydrogen jets were pushing the object, creating the non-gravitational acceleration without a visible coma. The problem: solid hydrogen is so volatile it is almost impossible to keep solid. The faint heat of starlight, even in deep space, should have evaporated the entire iceberg long before it ever reached us. It likely could not survive a journey of millions of years. Theory 2, the nitrogen splinter. A more recent and popular idea is that Oumuamua was a splinter of a larger Pluto-like planet from another star system. Pluto in our own system is covered in glaciers of solid nitrogen. If a giant impact shattered an exo-Pluto, it could send nitrogen ice fragments flying. Like hydrogen, nitrogen gas is also invisible. This is more stable and could possibly survive the journey. It would look like a dark solid surface, but it would still release invisible gas under the sun's heat, explaining the acceleration. Theory 3, the artificial origin. Avi Loeb. This is the most famous and controversial theory. Avi Loeb, a senior astronomer at Harvard University, pointed out another way to accelerate without gas use: the sunlight itself. Sunlight exerts a tiny amount of physical pressure called solar radiation pressure. It's what pushes a solar sail. However, this pressure is extremely weak. For it to push something as big as ʻOumuamua, the object would have to be very large in area, incredibly unnaturally thin. Loeb calculated that if ʻOumuamua was not a cigar but a flat pancake, and if it was less than a millimeter thick, the pressure of sunlight alone could explain its acceleration. He argued that while it could be a natural shard of material, an object with these properties was also consistent with being an artificial light sail, a piece of technology created by an alien civilization. This idea caused an enormous debate. Most scientists believe a natural explanation like the nitrogen iceberg is far more likely, but Loeb maintains that we cannot simply ignore the data just because it makes us uncomfortable. ʻOumuamua was so strange that all theories, even artificial ones, had to be considered. The second visitor, Borisov 2019, a relief. It looked like a real comet. It had a coma, had a tail. For 2 years, the bizarre nature of ʻOumuamua haunted astronomers. Was it a freak of nature? Was it alien? Was our first interstellar visitor just a puzzle we would never solve? Then, in August 2008, an amateur astronomer in Crimea named Gennady Borisov, using his own homemade telescope, spotted a new fuzzy object. He tracked it, calculated its orbit, and realized it was also hyperbolic. It was another visitor. The entire astronomical community held its breath and pointed its telescopes. And then a collective sigh of relief. The new object named by Borisov looked normal. It was everything ʻOumuamua was not. It was big, bright and fuzzy. It had a massive dusty coma stretching thousands of miles across. As it got closer to the sun, it grew a long, beautiful tail. This was without a doubt an interstellar comet. This was a profoundly important discovery. It proved that ʻOumuamua was not the only kind of visitor. It confirmed our theories that other star systems build and eject comets that look just like the ones in our own solar system. It was the normal one we had been expecting all along. Or so we thought, but still different its chemistry. Unusually high carbon monoxide CO content. The wonderful thing about a comet is that its coma, the gas cloud, is a direct sample of the stuff it's made from. By using spectroscopy breaking the light from the coma into its chemical rainbow, astronomers can read its ingredients list from millions of miles away. When they read the label on Borisov, they found another shock. Borisov's coma was drenched in carbon monoxide. Carbon monoxide is a very common ice in the universe, but it's extremely volatile. It turns to gas at incredibly cold temperatures around minus 250 degrees Celsius or minus 420 Fahrenheit. In our solar system's comets, water is the main ingredient. Carbon monoxide is usually a very minor component, frozen in with the water ice. Borisov was the opposite. It had some water, but it had a huge amount of carbon monoxide, far more than any of the thousands of comets from our own solar system we have ever studied. This was not just a little different. This was a fundamentally different recipe for a comet. Implications. It formed in a much colder place than our comets. Evidence for the diversity of star systems. The high level of carbon monoxide told us a fascinating story about where Borisov was born. For a comet to hold on to that much of such a volatile gas, it must have formed in a place that is unbelievably cold. It must have come from a region in its home star system that is much, much colder and farther out than our own Kuiper belt where our comets form. This was the first time we held a piece of another solar system in our hands, our telescopes, and could analyze it. The chemistry of Borisov was direct physical proof that the building blocks of planets and comets in other systems are chemically different from our own. Perhaps Borisov was born in the vast outer darkness of a star system much larger than ours, or perhaps it was born around a tiny dim red dwarf star whose habitable zone is so close that the rest of the system is plunged into a permanent deep freeze that allows for the creation of carbon monoxide-rich worlds. Whatever its origin, Borisov proved that other star systems are not just copies of our own. They are diverse exotic chemical factories that can build objects we have never imagined. The third visitor. 3I, Atlas 2023, the newest guest. Again, it is different. After the 1-2 punch of ʻOumuamua the weirdo and Borisov the chemically alien comet, astronomers knew the new age of interstellar astronomy was here to stay. They didn't have to wait long. In 2023, the third confirmed visitor was spotted. This time it didn't look like ʻOumuamua, And it didn't look like Borisov. Once again, it was something entirely new. It was designated 3I Atlas, named after the system that found it. And its defining characteristic was not its shape or its chemistry, but its behaviour. It was wildly unstable. Discovery found by the Atlas system, designed to find asteroids. The object was discovered by the Atlas Survey, which stands for Asteroid Terrestrial Impact Last Alert System. This is a set of robotic telescopes also in Hawaii whose main job is to scan the entire visible sky every few nights. It is designed to find objects moving in the inner solar system, specifically ones that might be on a collision course with Earth. Like ʻOumuamua, this object was flagged by the system's software because its speed and trajectory were wrong. It was another hyperbolic traveller. By now, astronomers knew the drill and quickly confirmed its interstellar origin. But as they watched it, 3I Atlas refused to behave. Behaviour unstable. It brightened then faded. Its activity was inconsistent. ʻOumuamua was steady and predictable in its fading. Borisov was also predictable, steadily releasing gas as it approached the sun just as a good comet should. 3I Atlas was chaotic. It was like a sputtering, failing engine. As it approached the sun, astronomers watched it suddenly flare up, becoming hundreds of times brighter over the course of just a few hours. Then just as suddenly it would dim, fading back to a faint, barely visible speck. It did this multiple times. This erratic behaviour is a sign of instability. It suggests the object was violently fragmenting. It wasn't just releasing gas smoothly like Borisov, it was likely carving or shedding massive chunks of ice and rock. These sudden breakups would expose fresh buried ices to the sun, causing a brilliant explosive flash of gas and dust, which would then fade as the gas cloud dispersed. It seemed that 3I Atlas was a dying visitor. It may have been a comet that was already fragile, and the thermal shock of approaching our sun for the first time in millions of years was the final straw. We weren't just observing a visitor, we were watching it tear itself to pieces in real time. Implications. Our sample M3 shows there is no typical ISO, each one is unique. This is perhaps the most important lesson so far. We have a sample size, an N of 3. We have seen 3 visitors from 3 different random star systems, and all 3 are completely different from each other. Visitor 1, ʻOumuamua, a dry tumbling strangely shaped object or exotic iceberg that accelerated without a visible coma. Visitor 2, Borisov, a normal-looking comet that was made of completely alien chemical materials rich in carbon monoxide. Visitor 2, 33I, Atlas. An unstable, fragmenting and self-destructing object that was breaking apart as we watched. If all 3 had been like Borisov, we would have concluded, okay, interstellar objects are just comets from other places. If all 3 had been like ʻOumuamua, we would be in a panic trying to understand what bizarre process creates these cigar-shaped rocks. But because all 3 are different, we have learned something much more profound. There is no typical interstellar object. The zoo of objects ejected by other star systems is incredibly diverse. It means that the processes that build solar systems across the galaxy are varied, chaotic, and creative. They produce stable comets, dry fragments, and unstable explosive shards. We have only opened the door. With new, more powerful telescopes coming online, we will soon go from finding one visitor every couple of years to finding them every few months. Each one will be a new messenger, a new piece of a different star system teaching us more about our place in a galaxy that is far stranger and more connected than we ever dreamed. When we analyse 3I Atlas, we move from the realm of astronomy into the realm of forensics. We are studying a refugee from a long-lost star system, and every piece of data tells a part of its story. The most dramatic and undeniable piece of evidence is its path. Its journey through our solar system is not a loop. It is a straight line bent only slightly by the sun's immense gravity. In astronomy, we measure an object's orbit using a number called eccentricity. An eccentricity of 0 is a perfect circle. Like Earth's orbit, though Earth's is slightly non-circular, an eccentricity between 0 and 1 is an ellipse. This is what planets, asteroids, and typical comets follow. They are all bound to the sun. An eccentricity of exactly 1 is a parabola, an escape trajectory. But 3I Atlas showed an eccentricity calculated to be as high as 1.0. This number is not just a hint, it is a scream. It confirms the object is on a hyperbolic path. It is fundamentally unbound from our sun. It is moving so fast that our star's gravity is little more than a speed bump. It will make its single blazing pass near our star and then be flung back out into the void, never to return in the lifetime of our species or even the lifetime of our planet. This path is a direct consequence of its incredible speed. We were already astonished by our first two interstellar visitors, ʻOumuamua and 2i Borisov. Borisov in particular was moving very quickly, confirming it came from far away, but 3i Atlas makes Borisov look like it is drifting. Its velocity relative to our solar system measured far from the Sun's gravitational influence is staggeringly high. This speed is perhaps the object's greatest and most telling mystery. Where could an object get this much energy? Things are not simply floating between the stars, they are actively thrown or ejected from their home systems. But the velocity we see in 3i Atlas suggests an ejection event of almost unimaginable violence. We are not talking about a gentle gravitational nudge from a passing star in its home system, which is how we think objects in our own Oort cloud get disturbed. We are likely looking at a gravitational slingshot of the highest order. Imagine a planet forming in a chaotic binary star system where two stars are orbiting each other. That young planet could be caught in a complex gravitational tug-of-war before being violently flung out like a stone from a catapult. Another more extreme possibility is an encounter with a supermassive black hole. If 3i Atlas passed too close to a large black hole, or even an intermediate mass one, it could have been accelerated to this incredible speed. However, there is another or perhaps more profound explanation. It might not have been a single violent event at all. It might be that 3i Atlas comes from a region of the galaxy that is simply dynamically hotter than our own quiet neighbourhood. Our Sun orbits the galactic centre in a relatively calm, stable and circular path. We live in the suburbs of the Milky Way within what is called the thin disk. But if an object originated in a much denser environment like the galactic bulge near the centre, or within a dense globular cluster where stars are packed tightly together, objects naturally move much faster relative to each other. If 3i Atlas came from such a region, its high velocity would not be the result of a special event. It would simply be its normal cruising speed, which just happens to be extreme compared to our own. This idea is supported by its inclination. 3i Atlas did not enter our solar system along the highway that all the planets and most asteroids use. This relatively flat highway is called the ecliptic plane. It is the disk of material from which our solar system was born. Atlas ignored this plane entirely. It dove in from almost directly above this plane, plunging toward the Sun at a very steep perpendicular angle. This high inclination is a classic signature of an outsider. It confirms the object has no ancestral relationship to our solar system's formation. Its path is a cosmic coincidence, a random intersection of its billion-year journey and our tiny spinning corner of the galaxy. If its path was the first shocking clue, its chemical makeup is the detailed confession of its alien origin. As 3i Atlas approached the Sun, the increasing heat began to do what it does to all comets. It vaporized the ancient ices on its surface. This process, called sublimation, creates a temporary atmosphere or coma of gas and dust around the object. This coma is a gift to scientists. By pointing our most powerful telescopes at the comet, we can capture the faint sunlight that shines through this coma. We then pass that light through an instrument called a spectrograph. This process splits the light into its fundamental barcode, or spectrum. Every chemical, every element absorbs and emits light at very specific colours or wavelengths. This barcode tells us exactly what the comet is made of, and the barcode of 3i Atlas looks like nothing we have ever seen before. Our own comets. Those from the Kuiper belt or the Oort cloud are predictable. They are mostly water ice, carbon dioxide ice, dry, ice carbon monoxide and dust. They are dirty snowballs. 3i Atlas is something else entirely. It is an alien artifact and we are reading its ingredient list. The first anomaly that jumped out to spectroscopic teams around the world was the clear signature of ammonia hydrate. While ammonia itself is seen in small amounts in our comets, this specific hydrated form ammonia molecules chemically bonded with water ice is very rare. Its presence suggests the object formed in an extremely cold environment, far colder than the regions where our own comets are believed to have formed. This points to an origin in the deepest, most frozen reaches of interstellar space, or perhaps a protoplanetary disk around its home star that was vastly different and much colder than our own. Alongside this, we found the building blocks of rock silicates. But again, these were not the simple primitive silicates we find in asteroids in our system. The light signature showed they were altered. They had been processed, perhaps cooked, by intense heat or radiation long before they ever entered our solar system. This could mean they formed very close to a star that was much hotter than our Sun, or perhaps they were exposed to a nearby supernova explosion early in their life. Even more exciting, we detected faint but clear traces of what appear to be complex organic molecules. We are not just talking about simple methane, we are talking about long-chain hydrocarbons, the kinds of complex carbon-based molecules that are the very building blocks of life as we know it. This object is a time capsule carrying the complex chemistry of another star system across the galaxy, and it flew right past our doorstep. But the truly bizarre data, the details that have theorists scratching their heads, came from the ratios of these chemicals. In science context is everything. The simple presence of a chemical is interesting, but its proportion to another chemical tells you the story of how it was made. In 3I Atlas, all the ratios are wrong. We measured the amount of cyanide, a molecule commonly found in comets, is relative to the amount of water. In our solar system, this ratio is fairly consistent. In 3I Atlas, the ratio was wildly different, suggesting it formed in an environment with a completely different chemical budget of carbon, nitrogen, and oxygen. However, the most baffling detail, the one that scientists are still arguing about, is what appears to be an inverted nickel-to-iron ratio. In our solar system and in our understanding of physics, iron is almost always more abundant than nickel. It's a fundamental rule of how stars forge heavy elements through fusion and in supernovas. In the dust grains analysed from 3I Atlas's coma, there appears to be more nickel than iron. This is so strange that many research teams rechecked their data, assuming it was an error. It was not. It is detail that is physically difficult to explain. It might imply an origin from a truly exotic type of star, perhaps a specific rare type of supernova remnant that forged elements in a way we don't fully understand. Or it could be that some strange chemical or physical process on the object's surface over billions of years preferentially held onto its nickel atoms while allowing iron atoms to be stripped away. Whatever the cause, it is a chemical fingerprint that screams, "I am not from around here." This object didn't just travel far, it travelled for a very, very long time. For its entire journey it was exposed. In the empty space between stars there is no magnetic field or thick atmosphere to protect it. For millions, or perhaps billions of years, it was constantly bombarded by high-energy cosmic rays, tiny particles accelerated to near-light speed by distant supernovas. This relentless space weathering leaves visible scars. It darkens the surface, turning a fresh icy grey colour into a dull reddish black. It also fundamentally alters the chemistry of the topmost layers, creating a kind of crust. The depth and specific nature of this processed crust on 3I Atlas tell us that it has been adrift in the interstellar ocean for an immense span of time. But how long the chemical models based on its exotic composition suggest something truly profound. The specific types of elements it contains and their ratios, even the strange ones, point to an incredible age. Computer models simulating its formation, trying to find a chemical recipe that matches our observations, keep pointing to one stunning conclusion. 3I Atlas may be up to 14 billion. Let that number sink in for a moment. The universe itself is estimated to be 13.8 billion years old. If these models are correct, 3I Atlas is not just a piece of another star system. It is a piece of one of the first generation of star systems. It is a relic from the dawn of the galaxy. This staggering idea connects all the pieces of the puzzle. It explains its composition, its speed and its inclination. Our galaxy has different parts. We live in the thin disk, which is rich in heavy elements and where stars like our Sun are relatively young. But surrounding this is an older, puffier, more chaotic region called the thick disk. Objects in the thick disk are ancient. They were formed when the Milky Way was just getting started before it flattened out. These ancient stars and any objects around them move on faster, more inclined orbits, plunging up and down through the galactic plane. 3I Atlas is not just a comet, it may be a planetesimal, a failed baby planet that was formed around one of the galaxy's very first stars. It was ejected from its nascent system and has been wandering the empty darkness for 14 billion years, a perfectly preserved ghost from the beginning of time. It is a messenger from an era when the universe was new, and by pure chance its ancient journey just intersected with ours. The discovery of objects like ʻOumuamua and Borisov did more than just add 2 new entries to our catalogues. They fundamentally changed our perspective on the universe and our place within it. For the first time we held in our hands, or at least in our telescope's viewfinders, a piece of another solar system. The implications of this are staggering, touching not just astronomy, but chemistry, biology, and even philosophy. We are finally beginning to get answers to questions we've barely known how to ask. Before these visitors arrived, all of our scientific models for how planets form were based on a single example, our own solar system. In statistics, this is called an n=1 problem. Imagine trying to understand all of humanity, all our diversity in culture, language, and biology by studying only one person. It would be impossible. You might conclude that all humans have brown eyes, or that everyone speaks English, or that the normal height is 5 feet 10 inches. You would have no concept of variety. This was precisely the situation for astronomy. We built comprehensive theories based on what we saw here. We had rocky planets Mercury, Venus, Earth, Mars close to the Sun, and giant gas planets Jupiter, Saturn farther out. We had 2 asteroid belts, one rocky one inside and one icy one, the Kuiper belt, on the edge. From this single example, we built the nebula hypothesis, the story of a spinning disk of gas and dust that slowly clumped together to form the planets we know. We assumed this was the standard way, the normal way for a solar system to be born. Then ʻOumuamua arrived. It shattered our assumptions. It didn't look like any asteroid or comet in our system. It was long and thin, perhaps shaped like a cigar or a flat pancake. It was rocky and dense, yet it accelerated away from the Sun without a visible comet tail. This non-gravitational acceleration was a puzzle. Our comets do this, ice turns to gas and acts like a tiny rocket engine, but ʻOumuamua had no visible gas. This single object forced us to ask new questions. Is it a new type of object we don't have, like a nitrogen iceberg from a distant cold star? Is it the fragment of a planet that was torn apart? Borisov was different. It looked more familiar, behaving like a comet. But when we analysed its chemistry, its recipe, it was also different. It had a surprisingly high amount of carbon monoxide gas, far more than typical comets from our own solar system. This tells us that the kitchen, where Borisov was cooked, its home solar system, is different from ours. It likely formed in a much colder, darker environment than our comets did. These samples of one n=1 from another system are incredibly valuable. They prove that our n=1 solar system model is incomplete. By studying them, we are forcing our computer simulations of planet formation to account for new outcomes. We are discovering that the galaxy is filled with a variety of solar systems that may be wildly different from our own. Maybe in some systems, giant planets form very close to their star. In others, maybe the raw materials are so different that Earth-like planets are impossible. These visitors are the first data points in a brand new field of science, the comparative study of solar systems. They are the first clues that help us understand the full range of possibilities the universe has for building worlds. For all of human history, studying other stars meant studying their light. We use telescopes to capture this light and spectroscopes to break it apart like a prism. This light tells us what a star is made of, how hot it is, and how old it is. But this is an indirect method. It's like trying to understand an entire unknown country by analysing the smoke coming from its chimneys. You can learn something, perhaps what they are burning, but you can't learn about their culture, their biology, or their geology. Interstellar objects are a profound breakthrough because they are not light. They are stuff. They are physical samples from those other countries, a piece of rock or ice delivered directly to our shores. This is why we call it galactic archaeology. Archaeologists dig up physical artifacts, pottery tools, bones to understand a past culture. We are now able to dig up metaphorically these interstellar objects to understand other solar systems. When we pointed our telescopes at Borisov, we weren't just looking at it, we were analysing the material it was shedding. We were reading the chemical ingredient list of the gas cloud it was born from billions of miles away and eons ago. Its high carbon monoxide content wasn't just a curiosity, it was a geologic clue. It told us about the specific temperature and density of its home nebula. Imagine a message in a bottle washing up on a beach. That bottle contains a sample of the sand, the air, and a leaf from the island it came from. This is what ISOs are to us. They are messages in bottles from other stars telling us what their islands are like. This new field allows us to test our theories directly. We believe that different types of stars produce different recipes of elements. For example, a star system with fewer heavy elements, what astronomers call metals, should produce chemically different comets and planets. We could never test this before. Now we can. If we find an ISO and can trace its path back to a specific metal-poor star, we can analyse the object's composition to see if it matches our predictions. These objects are time capsules. They have been travelling through the freezing void of interstellar space for millions, perhaps hundreds of millions of years. In that deep freeze, their original chemistry is perfectly preserved. They are pristine samples of the building blocks of planets from another part of the galaxy. By studying them, We are in a very real sense conducting remote geology and chemistry on a world we will never ever see. We are beginning to build a library of the different planetary DNA that exists throughout the galaxy. Perhaps the most profound question these visitors raise is about life. Where did the ingredients for life on Earth come from? The leading theory, often called comet delivery, or a version of panspermia, suggests that the building blocks of life were not made on Earth but were delivered to Earth. In the early chaotic days of our solar system, comets and asteroids rained down on the young planets. We have analysed comets from our own system, like in the Rosetta mission, and meteorites that have landed on Earth. We have found that they are rich in two crucial things: water in the form of ice and complex organic molecules. These prebiotic, meaning before life molecules, include things like amino acids, which are the fundamental building blocks of proteins, and nucleobases, which are the rungs on the ladder of DNA. The theory is that these comets and asteroids seeded the barren early Earth with the water for our oceans and the raw chemical ingredients needed to spark life. Now apply this idea to interstellar objects. If our comets are full of life's ingredients, what about their comets? When we studied Borisov, scientists were desperately looking for these same complex organic molecules. The data was limited, but the possibility is electrifying. If an interstellar comet like Borisov is also found to be rich in amino acids, it would imply that the building blocks of life are not unique to our solar system. This has deep philosophical implications. It would suggest that these ingredients are common or universal. It would mean that the seeds of life are being mixed and scattered throughout the entire galaxy. This is the core idea of panspermia, a Greek word meaning seeds everywhere. Interstellar objects are the delivery mechanism. We now know for a fact that material from one solar system can and does travel to other solar systems. We have seen it happen. The galaxy is not a collection of isolated islands, it's a dynamic system where material is constantly being exchanged. If the building blocks of life are everywhere and the delivery system ISOs is constantly scattering these seeds, then it's possible that any planet with the right conditions, liquid water, a stable star, a protective atmosphere, could have life begin. It makes the universe seem less empty and sterile and more like a fertile garden with the potential for life being sown in countless star systems over billions of years. These objects transform the origin of life from a purely local chemical mystery on Earth to a galactic-scale process of transportation and seeding. We may be related not just to the life on this planet, but to the chemistry of a star system hundreds of light years away. For all the excitement they cause, studying these objects is incredibly difficult. It is a true race against time. The problem has three parts. First, they are faint. These are not giant planets. ʻOumuamua was estimated to be only a few hundred meters long, the size of a city block. Borisov was larger, maybe a few kilometers, but that is still tiny on a cosmic scale. They don't produce their own light. We only see them because they faintly reflect the light of our sun. By the time they are far away, they are one of the faintest things a telescope can possibly look at. Second, they are fast. They are not bound by our sun's gravity. They are speeding through our system at incredible velocities, tens of kilometers per second. ʻOumuamua, for example, was traveling at over 26 kilometers per second, about 58,000 miles per hour relative to the sun. They are bullets, not guests. Third, because they are faint and fast, they are transient. They don't stay long. Our window of opportunities to study them is desperately short. From the moment one is identified as interstellar, we may only have a few months or even just a few weeks before it flies so far away from Earth and the Sun that it becomes too faint for even our most powerful telescopes like Hubble or the James Webb Space Telescope. This challenge creates an amazing fast-paced culture of global collaboration. The moment an object is flagged by an observatory like Pan-STARRS, which found ʻOumuamua as having a hyperbolic orbit, meaning its an unbound visitor alerts go out across the entire world. There is no time for competition. Astronomers in Hawaii, Chile, Spain, and around the globe immediately mobilize. They will often drop their own planned observations, research they may have waited months for, to immediately point their telescopes at this new target. It's an all-hands-on-deck emergency. Data is shared instantly on global networks so that another astronomer thousands of miles away can pick up the observation as the Earth turns. Space telescopes are retasked. It is a beautiful example of the global scientific community working as one, united by the thrill of discovery and the pressure of a ticking clock, all to squeeze every possible photon of light from this fleeting messenger before it disappears back into the dark. Observing these objects from Earth is a scramble. We are essentially studying a priceless artifact as it flies past us at high speed. We can never get a really good look, but what if we could? What if we could visit one? This is the next great frontier. But we have a problem: we can't chase them. ʻOumuamua was moving so fast that by the time we even found it, it was already past the sun, and heading out there was no rocket on Earth that could have been launched to catch up with it. It was simply impossible. If we can't see them, we must intercept them. We have to prepare for the next visitor. This is the brilliant concept behind new missions, most notably the European Space Agency's Comet Interceptor. The idea is simple. We can't launch a rocket after we find the target because it will be too late, so we must launch the rocket first. The Comet Interceptor mission planned for launch in the coming years will be a ready-to-go probe. It will be sent into space and placed in a stable parking spot 1 million miles from Earth at a location called Lagrange Point 2 or L2, and there it will hibernate waiting for a signal. Meanwhile on Earth, new more powerful observatories like the Vera Rubin Observatory in Chile will be scanning the sky every night. These new telescopes are so powerful, they are expected to find many more interstellar objects, perhaps several per year. The plan is this. The Vera Rubin Observatory finds a new interstellar object. Astronomers quickly calculate its path. If that path is reachable by our parked probe, the signal is sent. The Comet Interceptor wakes up, fires its engines, and begins a journey that may take months or years to fly to a precise point in space. Its goal is to arrive at that point at the exact same time as the interstellar object, allowing it to perform a flyby. This would be a monumental achievement. The probe would fly past the object or even through its gassy tail, its coma, taking high-resolution pictures and sniffing its chemistry directly with onboard instruments. It would be our first in-person encounter with an object from another star system. It would give us data thousands of times more detailed than anything we can get from Earth. We would finally be able to read the message in the bottle up close. This is the future, not just waiting for samples to wash up on our shore, but actively sailing out to meet them as they arrive. The appearance of interstellar visitors like ʻOumuamua and Borisov was startling, forcing us to consider our place in a galactic neighbourhood. They were mysterious, brief and alien, but their ghostly appearance, faint comas, icy compositions was also deeply familiar. They looked for all the world like comets. Before we could truly understand these guests from other stars, we first had to master the study of our own. Our solar system is filled with its own family of icy travellers. These are not visitors from afar, but our own cosmic cousins, born from the very same swirling cloud of gas and dust that formed the Earth and all the other planets. For millennia, they have drifted in the darkness of the outer system, visiting the sun's warm neighbourhood only occasionally. These local comets were our first introduction to the chaos and beauty of the cosmos beyond the predictable paths of the planets. They were the key that unlocked our understanding of the solar system's true scale, its laws of motion and its deepest origins. What then has this family of icy wanderers taught us? They taught us to replace fear with reason, and in doing so they showed us a snapshot of our own creation. Human history of comets, from omens to understanding. For nearly all of human history, a comet was not an object, it was a message. The night sky was supposed to be a symbol of perfection and eternity. The sun rose and set, the moon waxed and waned. The wandering stars, the planets moved with a complex but reliable rhythm along a set path known as the ecliptic. This celestial clockwork was predictable, it was safe. A comet shattered this safety. It would appear suddenly without any warning. It obeyed none of the rules. It could blot out a constellation appearing anywhere in the sky. It looked angry. The very word comet comes from the Greek kometes, meaning long-haired, and this hair was seen as the celestial banner, a bloody sword hanging over the world, or the weeping hair of a mourning god. When a comet appeared, civilizations panicked. It was a universally bad sign, a disaster, literally bad star. Ancient Chinese astronomers kept meticulous records of comets, viewing them as signs of celestial imbalance that could foretell the fall of a dynasty or a coming war. In Europe, they were blamed for everything. If a plague swept through a city, if a king died, if a harvest failed, people would point to the recent comet as the obvious cause. This terror is famously captured in the Bayeux Tapestry, which chronicles the Norman conquest of England in 1066. In one panel, a crowd of Englishmen points in terror at a brilliant star-like object with a fiery tail. This object we now know was Halley's Comet. To the people of the time, it was a clear omen, and indeed soon after its appearance, their King Harold was defeated and killed at the Battle of Hastings. The comet did not cause the defeat, but it became forever linked with the fall of a kingdom. This worldview was built on the ideas of the ancient Greek philosopher Aristotle, who argued that comets could not be in the perfect heavens. He concluded they must be atmospheric phenomena like lightning or rainbows, fiery emissions of gas high in Earth's atmosphere. For almost 2,000 years this idea held. Comets were seen as local, unpredictable and terrifying omens. The paradigm shift. The shift from terror to understanding did not happen overnight. It required three of the greatest minds in scientific history. First was Tycho Brahe, a Danish nobleman, and the greatest observational astronomer of his time. In 1577, a great comet appeared so bright it was visible in the daytime. From his state-of-the-art observatory, Uraniborg, Tycho set out to do something revolutionary: measure the comet's distance. He used a concept called parallax. You can see parallax yourself. Hold your finger out at arm's length, close your left eye and note where your finger is against the background. Now switch eyes, closing your right and opening your left. Your finger appears to jump against the distant background. This is parallax. The closer an object is, the more it jumps. Tycho reasoned that if the comet was close in the atmosphere as Aristotle claimed, then observers in different cities across Europe would see it against different background stars at the same time. But when Tycho compared his own meticulous measurements with those of other astronomers, he found the comet showed almost no parallax at all. The only possible conclusion was that the comet was not in the atmosphere. It was at minimum further away than the Moon. This was a profound discovery. It shattered Aristotle's model and proved that the heavens were not perfect and unchanging. A new object had appeared in the realm of the planets. Tycho didn't know what it was, but he knew where it was in deep space. The second mind was Sir Isaac Newton. Decades later, Newton developed his universal law of gravitation. He demonstrated that the same force making an apple fall to Earth was also the force keeping the Moon in orbit. He proposed that this gravity applied to everything, including Tycho's distant comets. Newton argued that comets were not chaotic wanderers. They were objects obeying the exact same laws as the planets. The difference was in their orbits. While planets moved in nearly circular paths, comets moved in extremely stretched out or elliptical paths. Gravity pulled them from the blackness of deep space. They whipped around the sun at incredible speed and gravity, then flung them back out again. They were not angry messengers. They were simply members of the solar system obeying the law of gravity. The third and final mind was Edmund Halley, Newton's close friend and the man who financed the publication of the Newton's world-changing book. Halley was fascinated by this idea. He began to compile all the reliable historical records of comet sightings. He focused on three specific comets, one seen in 1531, one in 1607, and one he had personally observed in 1682. Using Newton's new math, Halley calculated the orbital path for each one. He was stunned by what he found. The paths were nearly identical. This led him to a radical and brilliant hypothesis. These were not three different comets. This was one comet returning again and again. The time between each sighting was roughly 6 years. In 1705, Halley published his findings and made one of the boldest predictions in the history of science. He declared that this comet obeying Newton's laws would return. If it should return according to our prediction about the year 1758, he wrote, "Posterity will not refuse to acknowledge that this was first discovered by an Englishman." Halley died in 1742, never knowing if his prediction was correct. As the 1750s wore on, astronomers across Europe began to wait. The year 1758 arrived and the sky remained empty. But Halley hadn't accounted for the gravitational pull of Jupiter and Saturn, which slightly delayed the comet's journey. Then on Christmas night 1758, a German amateur astronomer named Johann Pallich spotted it had returned. The shift from fear to order. The arrival of Halley's comet, as it was soon named, was the single most important moment in our relationship with the cosmos. It was the final triumphant confirmation of Newton's universe. The comet, once the ultimate symbol of divine unpredictable wrath, had been tamed by human reason. The universe was not a chaotic place run by the whims of angry gods. It was a clock. It was a grand, magnificent machine, and its gears moved according to laws that the human mind could discover, understand, and use to predict the future. This shift was total. A disaster in the sky was transformed into a testament to order. We had gone from cowering in fear of the long-haired star to greeting it by name as an old familiar friend. The great memories. With the fear gone, comets became sources of intense public fascination and scientific wonder. Some apparitions have become cultural touchstones, moments when the whole world stopped to look up. Halley's Pearl Comet. The cultural icon. No comet is more woven into our culture than Halley's. Because its 60-year orbit is just about the length of a human lifespan, it has become a celestial baton passed from one generation to the next. The American author Mark Twain was famously born in 1835, the same year the comet appeared. He often said, "I came in with Halley's Comet. It is coming again next year, and I expect to go out with it." He was right. He died on April 21st, 1910, just one day after the comet made its closest approach to the Sun. But the 86 return of Halley's Comet was different. For the first time, we would not just wait for it, we would go to it. A cooperative fleet of spacecraft known as the Halley Armada was launched by the Soviet Union, Japan, and the European Space Agency. The most ambitious of these was the European probe Giotto. Its mission was to fly daringly close to the comet's heart or nucleus. On March 13, 1986, Giotto flew to within 100 kilometers of the nucleus, traveling at a speed 50 times faster than a rifle bullet. It was a suicide mission. Scientists knew the probe would likely be destroyed by the blizzard of dust and ice particles. And indeed, seconds before its closest approach, a particle impact knocked the camera offline. But not before it had sent back the first ever close-up images of a comet's core. The images were stunning. Scientists had long subscribed to the dirty snowball model proposed by astronomer Fred Whipple. They expected a bright reflective ball of ice. What Giotto saw was the opposite. The nucleus was one of the blackest objects ever seen, as dark as velvet or coal. It was not a dirty snowball, but a snowy dirt ball. This dark colour was a thick crust of organic dust, carbon-based molecules baked together by eons of solar radiation. The ice was buried underneath this crust. As the comet neared the Sun, this ice would heat up, burst through weak spots in the crust, and erupt into space as brilliant jets of gas and dust. Halley's Comet was not just a passive object, it was an active, dynamic, and surprisingly dark world. The 1990s, Hyakutake and Hale-Bopp. For those who were old enough to see them, the mid-1990s were a golden age. We were treated to not one but two of the greatest comets of the 20th century. First in 96 came Comet Hyakutake. This was the surprise comet discovered by an amateur astronomer just months before it peaked. Hyakutake's claim to fame was its proximity. It passed incredibly close to Earth, one of the closest comet flybys in over 200 years. Because it was so close, it appeared to move visibly against the background stars night after night. Its tail was enormous, stretching across half the sky, but its most beautiful feature was its colour, a ghostly ethereal blue. This was its ion tail. A comet typically has two tails. One is the dust tail, made of tiny solid particles like sand that are pushed gently by sunlight and curve along the comet's orbital path. This tail is typically white or yellow. The second is the ion tail, made of gas. The sun's intense ultraviolet light strips electrons from the gas particles like carbon monoxide, causing them to glow with a characteristic blue light. This tail of ions is then blown straight back by the solar wind, a stream of particles flowing from the sun like a windsock in a gale. Hyakutake's ion tail was one of the longest and most vivid ever recorded. Then, just as Hyakutake faded, astronomers knew something even bigger was coming. Discovered in 1995, Comet Hale-Bopp was the great comet of the century. It was found when it was still out beyond the orbit of Jupiter. To be visible at all from that distance meant one thing: it was colossal. Its nucleus was estimated to be 40 to 60 kilometers across dwarfing Halley's, which is about 15 kilometers long. This early discovery gave the world a 2-year warning. When it finally arrived in 1997, it was the main event. It was not as close as Hyakutake, but it was intrinsically absurdly bright. It was so bright it could be seen from the middle of light-polluted cities like Chicago or London. It was visible to the naked eye for a staggering 18 months, shattering all previous records. Hale-Bopp was the perfect textbook comet. It displayed both of its tails with magnificent clarity, the bright white curving dust tail and the dimmer blue straight ion tail. For all of 1997, it hung in the northwest sky after sunset, a celestial king holding court for the entire planet. Public awe and the dark side. The 1990s comets were a global phenomenon. The internet, then in its infancy, exploded with websites where people shared their amateur photographs. Telescope sales boomed. It was a moment of profound shared awe. But Hale-Bopp's magnificent lingering presence also had a tragic postscript. It proved that even in our modern scientific age, the shift from fear to order is not always complete. The old superstition of comets as messengers, as vehicles of disaster, returned in a new form. A small secretive UFO cult in San Diego called Heaven's Gate came to a horrifying conclusion. They believed that a gigantic alien spaceship was following Comet Hale-Bopp, hiding in its bright tail. They believed this ship was coming to rescue them, to take their souls to a level above human before the Earth was recycled. In March 1997, as Hale-Bopp shone at its brightest, 39 members of the cult committed mass suicide believing they were shedding their containers to rendezvous with the ship. It was a chilling reminder that the human brain that can calculate an orbit with precision is the same brain that can be seduced by superstition. The comet was a beautiful object of scientific study, but for some it was still an omen, a sign that meant the end of the world. Comets as time capsules. Beyond their beauty and history, comets hold a scientific importance that is difficult to overstate. They are not just cosmic cousins, they are our solar system's fossils, leftovers from formation. To understand why we must go back 4.5 billion years, our solar system was born from a vast spinning cloud of gas and dust called the solar nebula. At the centre, pressure and temperature grew so intense that our sun ignited. Near the hot young sun, only heavy dense materials could survive. Rock and metal condensed, clumping together to form the rocky inner planets Mercury, Venus, Earth and Mars. But further out in the cold depths of space beyond the frost line, the solar system was a completely different place. It was so cold that volatile light materials, things we know as gases on Earth, were frozen solid. Water ice, carbon dioxide ice, dry ice, ammonia ice and methane ice could all condense and clump together. These frozen ices mixed with bits of rock and black carbon dust formed the cores of the giant planets Jupiter, Saturn, Uranus, Neptune, but they also formed billions of smaller icy bodies. These are the comets. While the planets have been baked by the sun, churned by volcanism and weathered by liquid water, the comets were not. The powerful gravity of the giant planets acted like a slingshot, throwing most of these icy bodies into two deep freeze storage areas at the edges of the solar system, the Kuiper Belt, a donut-shaped ring of icy objects just beyond the orbit of Neptune. This is the home of short-period comets which orbit the sun in less than 200 years. The Oort cloud, a theoretical massive spherical shell of trillions of comets that surrounds the entire solar system, stretching almost a light-year into space. This is the home of long-period comets like Hale-Bopp, which take thousands or even millions of years to orbit the sun. Because they have spent 99.9% of their lives in this frozen, dark, pristine environment, they have not changed. They are perfectly preserved samples of the original ingredients that built our entire solar system. A comet is a 4.5 billion-year-old time capsule. To study one is to study the raw material of Earth itself. The Rosetta mission. Touching a time capsule. For decades we studied these time capsules from afar, but how do you open one? The answer was one of the most ambitious space missions ever conceived, the European Space Agency's Rosetta mission. Launched in 2004, Rosetta's goal was not to just fly by a comet like Giotto did. Its goal was to move in with one. It would chase a comet, match its speed perfectly and enter into orbit around it. It would then escort the comet as it journeyed toward the sun, watching it wake up in real time. Its target was Comet 67P Churyumov-Gerasimenko, a short-period comet from the Kuiper Belt. The journey took 10 years. When Rosetta finally arrived in 2014, the first images of 2P were bizarre. The nucleus was not a ball or a potato. It looked unmistakably like a rubber duck. It was clearly two separate objects, two planetesimals that had gently bumped into each other billions of years ago and fused together. Rosetta orbited this strange double-lobed world for 2 years, sniffing the gas and tasting the dust that erupted from its surface. It saw rugged cliffs, vast plains of dust, deep sinkholes and boulders the size of houses. It was not a simple snowball, it was a complex, active geological world. The mission's most dramatic moment came in November 2014. Rosetta deployed a small lander named Philae to touch the comet's surface. The landing was pure drama. The comet's gravity was so weak that Philae was designed to fire harpoons to anchor itself, but the harpoons failed. The lander hit the surface, bounced a kilometre back into space, bounced again and finally came to rest in a shadowy crevice. Despite the rough landing, the mission was a spectacular success. Rosetta and Philae revolutionised our understanding of comets. They found surprising water. We have long believed that Earth's oceans were delivered by comets and asteroids. Rosetta tasted the water ice from 67P by measuring its chemical signature, specifically the ratio of heavy water or deuterium to normal water. It found that 67P's water was a different flavour than Earth's ocean water. This suggests that asteroids, not comets like 67P, may have been the primary delivery vehicles for Earth's water, the building blocks of life. Most importantly, Rosetta found complex organic molecules all over the comet. It didn't just find simple ices like methane, it found glycine, which is an amino acid. Amino acids are the building blocks of proteins, the essential machinery of all life on Earth. This was the ultimate discovery. The time capsule was opened, and inside we found the very ingredients for life. Rosetta's grand finale came in 2016. As the comet headed back into the cold outer solar system, the probe's solar panels could no longer get enough light. ESA controllers sent it on a final one-way command, a slow controlled descent to the surface. It crashed onto the comet it had called home for 2 years, sending back data and ultra-high-resolution pictures until the very last Macinda. The Rosetta mission was a triumph. It transformed comets from abstract lights into tangible, complex places. It confirmed they are fossils of our birth, and it showed us that these icy wanderers are dusted with the very same organic compounds that 4 billion years ago on Earth may have sparked into life. Our cosmic cousins, it turns out, may also be our distant ancestors. Comets are not just beautiful passive objects. They are travellers moving with incredible purpose, and sometimes their path intersects with ours. When this happens, a comet ceases to be an astronomical curiosity and becomes an agent of destruction on a scale that is difficult for the human mind to comprehend. The danger: huge kinetic energy, high velocity. The primary danger from a comet is not its poison gas or its icy composition. The danger is its immense kinetic energy. Kinetic energy is the energy an object has because of its motion. The formula for it in simple terms is 1/2 multiplied by the object's mass multiplied by its velocity squared. This velocity squared part is the most terrifying component. Comets move unbelievably fast. A comet originating from the Oort cloud can approach the Sun at speeds exceeding 100,000 kilometers per hour or even faster. Because its speed is squared in the energy equation, a small increase in speed leads to a massive increase in destructive power. Think of it this way: a baseball mass thrown by hand is annoying. The same baseball fired from a cannon mass plus high velocity is lethal. Now imagine that baseball is a mountain of ice and rock, perhaps 10 kilometers wide, moving 50 times faster than a rifle bullet. When an object with this much energy hits a planet, it doesn't just make a crater. It explodes. The kinetic energy is instantly converted into a blinding flash of heat and light and a shockwave that circles the entire planet. The energy released can be thousands or even millions of times greater than all the nuclear weapons on Earth combined. This is not a collision, it is a sterilization event. Witness Shoemaker Levy đâm vào sao Mộc 1994, chúng ta đã thấy những vết sẹo. For most of human history, this threat was purely theoretical. Then in 1994, humanity watched it happen. We became witnesses. A comet named Shoemaker-Levy 9 had been discovered the year before. It had already had a hard life. It passed too close to the giant planet Jupiter, and Jupiter's immense gravity acted like a tidal force, tearing the comet into more than 20 pieces. These fragments, some over a kilometre wide, were famously described as a string of pearls orbiting the gas giant. Their orbit was not submual. Astronomers calculated that in July 1994, the entire string of fragments would slam into Jupiter one by one. For the first time, telescopes all over the world and the Hubble Space Telescope in orbit were pointed at a single target waiting for an impact. We did not see the initial impacts themselves as they occurred on the side of Jupiter facing away from Earth. But as the planet rotated, the impact sites came into view. What we saw was stunning. The impacts left giant dark circular scars in Jupiter's thick atmosphere. These were not small spots, they were enormous bruises, clouds of debris and superheated gas dredged up from deep within the planet. The largest of these scars, from a fragment designated G, was larger than the entire planet Earth. Scientists estimated the energy released by this one fragment alone was equivalent to 6 million megatons of TNT. This was hundreds of times more powerful than the world's entire nuclear arsenal detonating at once. We had watched in real time a planetary-scale bombardment. The message was clear: this was not science fiction. This happens. The solar system is a shooting gallery, and sometimes the planets get hit. The dark scars on Jupiter served as a profound warning for our own small blue world. Sự kiện Chicxulub Slope kể hủy diệt khủng long, đó là tiểu hành tinh hay sao chổi cuộc tranh luận về một sao chổi chu kỳ dài. 66 million years ago, a day on Earth began like any other. It ended with a global apocalypse. This event, known as the Chicxulub impact, caused the Cretaceous Paleogene or KPG mass extinction, wiping out 75% of all species on Earth including the non-avian dinosaurs. We know what happened. A celestial body measuring between 10 and 15 kilometers across struck the planet in what is now the Yucatan Peninsula in Mexico. The impact gouged a crater 180 kilometers wide and 20 kilometers deep. The immediate effects were catastrophic. The impact triggered a mega tsunami thousands of meters high that raced across the oceans. It threw trillions of tons of superheated rock and dust into the atmosphere. This material rained back down all over the globe, heating the air so much that it likely ignited global firestorms, cooking any animal not sheltered underground or underwater. But the worst was yet to come. The fine dust and soot from the fires blocked the sun, plunging the Earth into a dark impact winter that lasted for years. Photosynthesis stopped. Plants died, the herbivores that ate them died, and the carnivores that ate the herbivores died. The food chain collapsed. For decades, the scientific consensus has been that this dinosaur killer was an asteroid from the main asteroid belt between Mars and Jupiter. Evidence like the layer of iridium, a metal rare on Earth, but common in asteroids found worldwide, points to this conclusion. However, a compelling debate continues: was it an asteroid or was it a comet? A competing theory suggests the impactor was a long-period comet. These comets come from the Oort cloud, the vast icy sphere of debris at the extreme edge of our solar system. The argument for a comet is based on statistics and physics. While asteroid impacts are more common, proponents of the comet theory argue that Jupiter's gravity can act like a giant cosmic slingshot. It can grab a long-period comet falling in from the Oort cloud, disrupt its orbit, and fling it into the inner solar system on a path that crosses Earth's. These comets are also typically larger and move much, much faster than asteroids. Because of that velocity squared rule, a long-period comet could deliver the same destructive energy as a much larger, slower asteroid. If the Chicxulub impactor was indeed a comet, it would mean that while such devastating events are rare, they can come from a direction we are not watching with a speed we are not prepared for. Whether asteroid or comet Chicxulub proves that our planet's history has been shaped by sudden violent death from above. Phòng thử hành tinh nhiệm vụ DART, chúng ta không còn bất lực. For 66 million years, the dinosaurs' fate was a lesson in helplessness. They had no telescopes, no space programs, no warning. They were simply erased. But we are different. We are the first species in our planet's history that can understand this threat. And now we are the first species that can do something about it. We are not helpless anymore. This new era of planetary defense was proven by NASA's DART mission. DART stands for Double Asteroid Redirection Test. The mission's goal was not to destroy an asteroid which could just create many smaller dangerous fragments, but to nudge it. The target was a small asteroid moonlet, named Dimorphos, which was orbiting a larger asteroid named Didymos. This system was very far away and posed no threat to Earth, making it the perfect target for a test. In September 2022, after a 10-month journey, the DART spacecraft, roughly the size of a vending machine, slammed head-on into Dimorphos at a speed of over 22,000 kilometers per hour. The result was a spectacular success exceeding all expectations. Telescopes on Earth watched as the asteroid system brightened significantly from the cloud of debris, and subsequent measurements confirmed the impact had altered Dimorphos' orbit around Didymos. It shortened the orbit by a full 32 minutes. DART proved that the kinetic impactor technique works. We successfully hit a small target millions of kilometers away, and we changed its path. While the technology is still in its infancy, the concept is proven. If we find a dangerous asteroid or comet decades in advance, a mission like DART, or perhaps a series of them, could give it the small push needed to change its trajectory, ensuring it misses Earth by a safe margin. We are no longer just passive observers, we are now active guardians of our planet, agents of creation. While comets are rightly feared as bringers of destruction, they have a second profound identity. They may in fact be the very reason we are here to fear them. These icy bodies from the deep solar system may be the agents of creation that delivered the essential ingredients for life itself. Mang đến sự sống sao chổi có thể đã mang nước và các hợp chất hữu cơ axit amin đến trái đất sơ khai. Let us rewind the clock over 4 billion years. The early Earth was a terrible place. It was a hot, molten and sterile ball of rock constantly bombarded by debris. It was almost certainly dry. So a fundamental question arises: where did our planet's vast, life-giving oceans come from? One of the leading hypotheses is that comets delivered our water. Comets are at their core dirty snowballs. They are made mostly of water ice frozen solid for billions of years. During the early solar system's chaotic late heavy bombardment, Earth was hit by millions of these objects. Each impact would have vaporized the comet's ice, releasing massive amounts of water vapor into the atmosphere, which would then cool, condense, and fall as rain. Over millions of years, this celestial rain could have filled the basins that became our oceans. Scientists test this idea by looking at the flavour of the water. Water H2O is made of hydrogen and oxygen, but there is a heavy version of hydrogen called deuterium. The deuterium to hydrogen ratio in Earth's oceans is a specific chemical fingerprint. If comets delivered our water, their water should have the same fingerprint. Missions like the European Space Agency's Rosetta, which visited Comet 67P, have measured this ratio. The results are complex. Comet 67P's water was very different from Earth's, with much more heavy water. However, other comets like Comet Hartley 2 seem to be a much closer match. The current scientific thinking is that comets definitely contributed to Earth's water, but they probably were not the only source. Asteroids which also contain ice likely played a major role as well. But water alone does not create life. You need something else: organic compounds. These are the complex carbon-based molecules that form the machinery of all living things. Comets are packed with this stuff. Protected in their deep freeze ice, they preserve a pristine sample of the original chemicals that formed our solar system. And when we look closely, we find more than just methane or carbon dioxide. We find amino acids. Amino acids are the fundamental building blocks of proteins. Proteins are the molecules that build our cells, digest our food, and carry out almost every function of life. In 2009, samples returned from NASA's Stardust mission, which flew through the coma of Comet Wild 2, confirmed the presence of glycine, the simplest amino acid. Since then, more complex organics and even sugars like ribose, a key component of RNA, have been detected in comets. Comets therefore acted as a cosmic delivery service, seeding the barren early Earth, not only with water, but also with the exact chemical toolkit needed to build life. Having the ingredients is one thing. Getting them to combine and ignite into life is another. This is the mystery of abiogenesis, the process of life arising from non-life. Comets may have played a role here too. They may have provided the initial spark. Imagine a comet striking the early ocean. It's not the planet-killing impact of Chicxulub, but a smaller, more common event. The comet delivers its payload of amino acids and other organics into the water, but it also delivers a colossal amount of energy from the impact's shockwave. Scientists have conducted experiments called shock synthesis, showing that the intense pressure and heat from an impact shockwave can force simple organic molecules to link together, forming more complex structures like the peptides that form proteins. In this scenario, comets are not just the delivery trucks, they are also the lightning bolt. They deliver the ingredients for the primordial soup, and simultaneously provide the jolt of energy needed to start the chemical cooking, forcing these simple bricks to build the first complex structures. The comets from the outer solar system, in their chaotic and violent arrival, may have been the very catalyst that sparked the long chain of events that eventually led to microbes, to plants, and ultimately to us. The cosmic duality. This brings us to the profound dual nature of comets. They are the ultimate symbols of cosmic chaos and creation. They perfectly represent the universe's indifference, its power to both give and to take away on a planetary scale. A comet is a taker of life. The dinosaurs looked up 6 million years ago and saw their doom arriving as a brilliant new star in the sky. The impact reset the evolutionary clock, ending a 50-million-year reign in a single day of fire and darkness. Comets are a reminder that our existence is fragile, balanced on a knife edge in a dynamic and often violent solar system. And yet a comet may also be the giver of life. 4 billion years ago, a sterile Earth may have looked up to see a sky full of shooting stars, comets that were delivering the very water we drink and the very carbon atoms that make up our DNA. The same type of event that ended one era may have been the exact event that began it all. Comets are the messengers that connect the cold, dead outer solar system with the warm, living inner planets. They demonstrate that in the universe, destruction and creation are not opposites. They are often two sides of the same coin. The death of the dinosaurs delivered by an impact paved the way for the rise of mammals, and thus for us. The violent, chaotic bombardment of the early Earth, a time of destruction, may have been the necessary crucible for life's origin. Comets, therefore, are not just ice and dust, they are a physical link to our deepest origins and a powerful warning for our future. We often look up at the night sky and feel a sense of profound stillness, a quiet separation. It is easy to imagine our solar system, our sun, our 8 planets, our belts of asteroids and comets as a self-contained unit. We feel it as a distinct, orderly system, an island of light and life in a vast, cold and empty ocean of black. We have our borders defined by the familiar orbits of the planets and the distant unseen cloud of our own comets. We feel safe within these borders, but this feeling, this sense of quiet isolation, is a beautiful illusion. The stillness we perceive is not the silence of an empty room. It is the quiet of a vast open coastline waiting for the next wave to arrive. Our solar system is not and has never been an island walled off from the rest of the universe. It is and always has been an open shore. For billions of years, we've been part of a cosmic exchange, a galactic flow. We just did not have the telescopes powerful enough to see the largest visitors arriving. We assumed the comets we tracked were our comets born in our own system, and forever bound to our sun. We thought the asteroids were our asteroids. But the island metaphor fails because an island has a clear boundary. Our solar system has no wall. The sun's gravity, our anchor, weakens with distance until it finally merges with the gravitational tides of the Milky Way galaxy itself. We are not stationary. We are moving through the galaxy, orbiting its massive center at hundreds of thousands of miles per hour. As we move, our entire system passes through different regions of interstellar space. We drift through the invisible remnants of ancient exploded stars, through cosmic clouds of dust, and through the unseen highways traveled by objects violently thrown out of other star systems. The shore is open, and the tide is always coming in. This tide, this constant galactic flow, is fundamental to our very existence. The universe is not a static collection of objects. It is a dynamic, evolving environment. Matter is in constant motion, a river flowing between the stars. The very elements that make up our planet, our bodies, and the air we breathe were created in the fiery hearts of stars that lived and died long before our sun was even born. This stardust drifted through the void, was pulled together by gravity, and eventually formed our sun, our Earth, and us. We are in the most literal sense made of the recycled material of the galaxy. This flow is ancient and continuous, but it is not just a gentle rain of basic elements of hydrogen gas or microscopic dust. The galaxy is also exchanging larger things. It is trading in rocks and ice. When solar systems form, they are messy, chaotic places. Young planets migrate, and their immense gravity acts like a cosmic slingshot, flinging smaller bodies, comets, and asteroids out of their home systems and into the deep dark of interstellar space. These objects then travel for millions or even billions of years, carrying a physical sample of their birthplace with them, a chemical postcard from another world. And now we are finally seeing them. We are standing on our shore and witnessing the proof. These visitors, these messengers from afar have arrived. We have seen them, the strange tumbling cigar-shaped ʻOumuamua, the more familiar icy comet Borisov, the fragments of Atlas. These objects are the flotsam from that galactic ocean, tangible proof of our connection to it. They are a profound reminder that we are part of a much larger, messier, and more wonderfully diverse story than we ever dared to imagine. Why messy? Because our own solar system appears relatively neat. We have our rocky planets close to the sun and our gas giants farther out. We have patterns we understand, but these visitors challenge our assumptions. ʻOumuamua looked like nothing from our home system. Its shape, its motion, and its dry, rocky nature suggested that the processes forming other worlds might be wildly different from our own. It tells us that the galaxy is not just making copies of our solar system. It is running countless different experiments at once. Some systems might be violent, flinging out fragments constantly. Others might be quiet. Some might be rich in the elements for life. Others might be barren. This incredible diversity is the larger story. We are not the protagonists of a solo play. We are just one character in a massive, sprawling ensemble cast, and we are only just beginning to meet the other actors. These objects are tangible fragments of other worlds. This is the most powerful realization of all. It is not just light from a distant star. It is a piece of that star's system. A rock from a place hundreds or thousands of light years away has drifted past our sun. It carries the chemical fingerprint of its parent star. It carries the physical history of its own chaotic formation. It is a message in a bottle written in a language of geology and chemistry that we are only just beginning to learn how to read. They force us to lift our gaze from our own local neighborhood and acknowledge our citizenship in the wider Milky Way. We are connected not just by gravity and light, but by a physical exchange of material. This cosmic perspective changes how we see the dark. So tonight, as you drift off to sleep, let go of the idea of the solar system as a safe, walled-off island. Instead, picture yourself standing on that open shore. Imagine these ancient silent travelers, these fragments of other worlds drifting through the darkness far beyond the orbit of Neptune, moving quietly between the stars. They are passing by right now. ʻOumuamua is already far away, heading back into the void. Borisov is leaving too, but more are coming, countless more. Each one carries a story of its birth star of a system we may never see. They are the physical threads connecting our small blue worlds to the entire sprawling and interconnected Milky Way. The stillness of the night is not empty, it is full of stories passing in the dark.